And this kind of goes back to all the legwork of, bless you. This goes back to all that legwork and all that vocab that you keep seeing. You say, even when we were doing quadratics, about terms in parentheses and zeros. Because if we know the relationship between zeros and terms, we can easily build polynomials. We can easily build polynomials. For example, if I say that you have zeros at -1, 3, and 4. If I say you have zeros at -1, 3, and 4, what will your terms be? What was that? Terms. What are the terms? Thank you. You were on the right track, but whenever we go to terms, we're talking about the actual the binomials. So your terms would be x plus 1, x minus 3, and x minus 4. Like I was saying, you're just working backwards. Start with the zeros, build the function. So if I'm going to build that function, what do I have to do with those three terms? Yeah, exactly. All the wavy thingy stuff. Just multiply out. If you remember when we did this before in the beginning of this section, I always said, hey, do those two first, because then it was easier to distribute that one out front than the other way. That's the best way to go about doing these. Okay? So we're building functions. So this is what, x squared minus 7x plus 12. And I have to distribute to that 10x plus 1. When I distribute the x plus 1, we're going to get what? X cubed squared and then just combine like terms. There's the polynomial, I think they call it polynomial of least degree containing polynomial. That just means you have 3 zeros, you should have how many? What should your degree be? It will also say leading coefficient positive more often than not. That way you don't have to worry about which value you make negative and things along those lines. Yes, sir. You know, I am so glad you asked that. Because guess what I was just going to show you? Imaginary. That was a great, you know what? It's like you knew what I was going to do. This is what you call the anticipatory question. If you can ever plant that when you know you're being observed, like tell a kid, hey, I need you to ask this question. At that specific moment, that is awesome. I've never done that. So we'll get to the imaginary one here in a second, but I want to show one more example of how the instructions are usually used. Write a polynomial function of least degree that has real coefficients in the given zeros and the leading coefficient is equal to 1. Right. That just basically means least degree, how many zeros do you have? Which means what degree should you have? 3. That'll be helpful. Okay. So if you have zeros of 3, 0, and -2, what are your terms? What term generates 3 as a 0? X minus 3. What term generates a -2 as a 0? X plus 2. What term generates 0 as a 0? X. I just put that up front. Okay. FOIL. X squared minus x minus 6. Distribute. And there's your function of least degree with the following zeros. It's a lot of distributive property. It's really, really, really straightforward. You have zeros, make the term. Working backwards. Okay. Working backwards. Now to the whole imaginary front. Like, okay. When you start thinking about imaginaries, how do you generate an imaginary zero? What did the term always have to be to get x squared, then what? Something. Good. In order to get an imaginary answer, that meant that it had to come from x squared plus something. Right? Whether that something was a 4 or a 1 or 49 or 25 or 36, whatever. It could be 8. It could be any value. What happens is you get, instead of a difference of squares, we're looking at a sum of squares. That's how you're always able to generate I. Now, when you get one I, don't i's always come in pairs? Yeah. They have to, because they're generated from the x squared. So if you're given zeros of 2 and 3i, what other zero is there that they just don't list? The negative 3i. Very good. So the negative 3i also has to be there. This is very, very common when they do imaginary values. It's hugely common. They're just saving ink, really, when that way they don't read. Right? Because i's have to come in pairs. They have to. Okay? If there's one, the other's there. They could list negative 2i, which means there has to be a positive 2i. They could say positive 2i root 3, which means there has to be a negative 2i root 3. It's those little things that'll happen. It's very, very subtle, but it's not tough. So you can do this one of two ways. This one's the easy. What's the term that generates a 2 for a 0? X minus 2. Okay. Now, to figure out this one, you can do it one of two ways. Since my zeros, what we've always done is we know that came from terms x minus 3i and x plus 3i. You think of it, kind of where they came from. But in order to get a 3i, what did you have to have? Yeah. A lot of times I like to use just square it. Square whatever that number is in front of the I and put a plus sign. That's how it's going to work. It's always going to work that way. So your terms would have been x minus 2 and x squared plus 9. You can go either way. Either way is going to work just fine. It depends on how you remember it. If you follow the pattern that zeros are created from terms by working backwards, it'll always work this way. Well, if you remember, like, okay, it had to be a squared term, it had to be a plus. What's 3 squared? That's really all it is. All right, and then you FOIL it out, and you get your polynomial of least degree, x cubed minus 2x squared plus 9x minus 18, and you would be happy. Polynomial of least degree. First term is positive. The coefficient of function. So not terrible, is it? So you were saying, like, what would you do? No, pretty simple. We hope. That's easy. A little different. We have zeros at 1, 2, and 1 plus I. Yeah, just 1 minus I. You were close. You were close. I didn't see the. I saw the minus I, but then you said. I saw you say 1. I thought you were like repeating yourself. I didn't see you say the plus I. No. So same idea. I's come in pairs. Okay? I's come in pairs. So if there's a 1 plus I, there has to be a 1 minus I. If there's a 3 minus I, there has to be a 3 plus I. If there is a negative 4 plus I, then there has to be a negative 4 minus there has to be a negative 4 minus I, and so on and so on and so on. Okay. So what should our degree of the polynomial be when we're done with this? Should be a fourth degree polynomial when we're done. Now these two guys are simple. We've got x minus 1, x minus 2. The next one is a little bit weird. I'm going to show you this. I'm going to show this long form first, and then see if we can come up with a shortcut. Now, again, remember they come in pairs, so that one has to be there. If we continue to follow the pattern of x minus r0, I get the following: x minus 1 plus I, and then I get x minus 1, minus I. Are we okay with that? All I'm doing there is I'm writing it out verbatim like we had there. I'm writing it out in terms of x minus my 0. Because that's kind of what we've been doing all along. From here, I'm going to kind of not worry about this side for right now, because that side's pretty easy. I just have to FOIL. I'm going to worry about what I have going on in here. Is it okay if I do this? Distribute the negative? If I distribute the negative both times, I'm going to get the following. Well, let me write it here. X minus 1 minus I, x minus 1 plus I. Are we okay with that? Do you guys remember what's called the associative property? Yeah. Associative property deals with how you group things over addition. It basically means that you can change your parentheses for your order of operations over addition or subtraction. It doesn't matter. It's how you group things, how you associate in groups. Kind of way of looking at it. Which means then technically I can do this, and it doesn't change anything. Okay? Watch what happens now. We get my bracket up here. I have x minus 1 minus I, x minus 1 plus I, and then these guys are still here. So when you think about it, that basically means I can FOIL the front two, and I can FOIL the back two. I don't want to FOIL those back two, because that's pretty ugly. Because if you think about it, isn't this? I know. You guys ever heard of a thing called U substitution? Has ever showed you that? Do you guys agree that this part right here kind of looks like crap? It does, though. It does. But within both of those two terms, they have something in common. What? X minus 1. So with this thing called U substitution, I'm going to let U equal x minus 1. I'm going to make something that looks like crap look neat and tidy. It becomes less, I don't know, less brainy or less hard on the brain. I can't. So if I let U equal x minus 1, bless you, that means anywhere I see that x minus 1, what am I going to put? U. So I get U minus I and U plus I. I'm worried about this part here. It just happened to be dumb luck that I had an x minus 1 there. We'll talk about it. Isn't that a difference of squares? difference of squares, isn't it? You get u squared minus I squared. What's I squared? -1. What's minus -1? +1. So basically what happens here is that by doing this, I know that this is now the quantity x minus 1 squared plus 1. So I have to just jump square back. And don't kill them. I wanted to show how. So now, from here, all that junk turns into a somewhat clean-ish trinomial. You get x squared minus 2x plus 2. Here, we're going to have x squared minus 3x plus 2, x squared minus 2x plus 2. And then, just unfortunately, this is a massive distributed problem. When you have that, you just got to be very cognizant of your signs. That's where people get messed up. It's not a tough thing to do by any stretch. Send your values across. A partridge in a pear tree. Remember though, as you go through it, the mapping of it is easy. It's just very, also happens to be pretty simple to get a dumb mistake. Okay. And then just rewrite one last time. X to the 4th, 5x cubed. Polynomial of least degree. I had 4 zeros, so happens one of the 4th degree polynomial. Now, excuse me, you guys were kind of going, in not so many terms or tone, but it's pretty good at the voice there. It's pretty close. All right. So when you get the values of like 1 plus I or 2 plus I, what any of those, it's always going to fall under the same exact pattern. Always. So if you wind up with 2 minus I as a 0, that means there's a 2 plus I, which means it's always going to be x minus 2 quantity squared plus 1. Okay. It's always going to be this. Because if you distribute through like we did, this same exact pattern occurs. You're going to get a difference of squares, and you're always going to wind up with minus I squared. Always. Minus I squared means plus 1. It always does that. Excuse me. What happens if you have this? if you're given something with a multiplicity, it means how many times does it occur? Twice. So if 3 is a 0 with multiplicity of 2, how many terms should I have that has a 0 of 3? 2. What's the term of 0 of 3? Yeah, you just have it twice. You want to make sure you saw that. So this would be x minus 2, x minus 3, x minus 3. It rang a bell a second ago when I mentioned that you want a multiplicity. I just want to make sure you saw what it would look like. Again, it's not tough. Multiplicities don't have to occur at 0. They could. It just means if you have multiplicity at 0, that just means it's going to be like x squared, x cubed, x to the 4th, or whatever. Hello. Same term twice. Has to be that means it's the same 0 multiple times. That's what that means. Because if it was x plus 3, x minus 3, those are two different zeros. Those wouldn't have multiplicity. It has to be the same number. Does that make sense? Let's try another one. Let's say we have 0. Let's try that real quick. Let's just do one more with those minus i's. See if we can follow the pattern. If I have 0 and 3 minus I, I'm going to write the polynomial of least degree. What degree should we wind up with? Third degree, very good. Should wind up with a third degree because I have a 0, a 3 minus I, which means I also have to have a 3 plus I, good. This one's easy. The other one, you remember the pattern. It's always going to be x minus whatever the value is here, quantity squared, plus 1. Always going to work. Okay. Now, you have to remember, that means x minus 3 times x minus 3. Because that's where most of you will just write, oh, it's x squared plus 9. So this becomes x cubed minus 6x squared plus 10x. Polynomial of least degree. Sorry, we raised that up a bit. Everybody's going like this. Yeah. Why is there what? Oh, we had a 0 at 0. Did you not see that? No, it's 0, not O. I know. Yeah, because what generates a 0 and 0? It's x. You just said it equal to 0. Sure. This one? This all the x plus x. I just spoiled that. So that was x minus 3, x minus 3. If you remember, there's special patterns that happen here. It's the first term squared, multiply the two together and double it, square the last term. And then we had to tack on the plus 1. The x was here. I have to distribute all that in at the end. So this guy should have had x on it. That's where it came. Fine time for math. So add these to what you got going on right now. We got 6, 7. Let's do. go 41 to 46. And then I want you to try 55. I want you to see if you can figure out how to use your graphing calculator to search for things within the table. Oh, it's so hard. So let's see. 41, you've got a 3i, negative 3i, so those are both taken care of. 42, you have a 2, negative 2, and a negative 6i, which means there has to be a positive 6i. 43, you have an I, negative 3i, and 3i, which means there has to be a negative I, and so on and so on. And so on. Okay. There's only one of them that has that trick of this guy here, but we should be okay to go. Okay. We'll get into the little bit of 6-8, 6-9 tomorrow. I don't see this being a big deal at all. We'll be done with this on Friday. I have absolutely no doubt. This is the last little bit of it. 6-8, 6-9 is a lot of just looking at tables in the calculator. We also do one other version of building the function if we're given zeros. Remember how we did the quadratic stuff? We had to search the A value in vertex form. Kind of the same basic idea for polynomials. It's the same functionality. Really quick. So tomorrow will probably take about 20 minutes tops. Go through those. I have a little extra review sheet. I'll have that printed out for you guys tomorrow. I just need a chance to get it morning because we're down like a 1.5 copy or something. For Friday, what I normally do with this unit, I do calculator, non-calculator. So we'll do that as well. Okay. Like when you get to the non-calculator one, I usually give you guys usually it's a build a function, and then I usually give you a synthetic problem for that. The rest of it is just going to be finding zeros, and it's kind of what we've been doing over and over again. You got multiple methods to be able to get through and search through. Yes, ma'am. Oh, what you're doing right now, build a function. It's when you give the zeros through, build a function. We're going to show another way of building the function out tomorrow when we get into different type of graph version. Yes, sir. Friday. We'll do it Friday. I was thinking about. I wasn't anticipating being this much out, and then yesterday you guys flew through it as quickly as you did. I wasn't worried about it. I wasn't really confident. How do you what? So I would put this in my calculator, and year 0 is 1980. Count to see where it hits that number. It's very similar when we did the quadratic stuff. It just happens to have a couple higher degrees. A lot of table work.